Uh, so yeah نحن في الفوكس ويا فوكس. السلام عليكم ورحمة الله وبركاته. ازيكم يا شباب؟ معاكم أحمد نبيل. بس نظبط الستابنا عشان أقدر آم، بس كده ننزل OBS بقى. طيب، إن شاء الله ده فيديو كده. ده نوع من المحتوى اللي أنا I'm into it lately. أنا الفترة الأخيرة مهتم بهذا النوع من المحتوى. وهو يعني إن حد أو قراءة شخص لكتاب ما. يعني كنت يعني أول ما تعرضت للنوع ده للمحتوى كان مع دكتور تشاك، معروف جدا بالكورسز بتاعت البايثون والسي بتاع جامعة ميتشيغان. فأنا حبيت الستايل ده من الفيديوهات، فحبيت أعمل الإصدار الخاص بيا my own version. ده كتاب ال OSTEP أو 3 Easy Bases OS بتاع الكورس، يعني بتاع جامعة مش فاكر اسم الجامعة بالظبط يعني، بس هي من أكثر الجامعات المرموقة يعني في CS. دي هتبقى قراءتي أنا للكتاب. الفيديو ده مش explanatory، مش تعليمي، مش توتوريال، مش شرح. أنا بس بذاكر أو بقرا الشابتر وهشارك يعني قراءتي يعني. لا أدري أصلا كنت هنشر الفيديو ده أو لأ، بس هو أنا بحب إنتاج المحتوى عموما، فده بيشجعني بالمرة أذاكر وبالمرة أعمل محتوى يعني. ف كوباية الشاي جميلة بقى، أنا مش معايا شاي دلوقتي. عملت رز مية و معايا تابلت عشان أحط حاجات كده. بس يلا بينا نبدأ. بسم الله. The abstraction, the process. الابستراكشن ده هي العملية بتاعت إنشاء layer من آه، إنشاء layer لتبسيط الكومبلكسيتي. ده فهم ليها، مثلا يكون في حاجة كومبلكس فيها بقى مثلا زي مثلا لوحة الكنترول بتاعة الطيارة كده، فيها أزرار كتير وحاجات كتير أوي، بس أنا مثلا مش هاممني منها غير. طبعا يعني حتى عارف اللي أنا بقول ده مخل يعني، بس يعني هو باك جراوند كومبلكس بعمل لها زي فور جراوند كده سيمبل، محاولة لتلافي أو تلاشي كل كومبلكسيتي أو التعقيد ده بلير من السمبlicity. زي الابستراكشن بتاع الكود او اللي هو الاو بي. بنعمل حاجة، بنقلل بنقلل الكومبلكسيتي الواضحة يعني، وبنحط لها abstraction يعني، زي ان احنا الموضوع بقى واصل يعني، مش مضطر اعمل كل ده. In this chapter we discuss one of the most fundamental abstractions that the OS provides to users, the process. The definition of a process formally is quite simple. Is a running program. The program in itself is a lifeless thing. It just sits there on the disk, a bunch of instructions and maybe some static data writing to spring into action. هو ال OS أو ال process تعرفة is a running program. يعني احنا بيبقى عندنا الستورج أو الديسك عليه البروجرام متخزن عليه. when it pops into action, springs into action، هذا البروجرام بتعمل منه instance. هذه الانستنس تسمى process واللي هي برنامج حي. طيب it's the operating system that takes these bytes and gets them running, transforming the program into something useful. It turns out that one often wants to run more than one program at once, For example, consider your desktop or laptop where you might like to run a browser, a web browser, mail program, a game, a music player, and so forth. I'll close the WhatsApp and come back again. Just a sec. عدنا من جديد. كنا واقفين عند ان it's the operating system that takes these bytes and gets them running, transforming the program into something useful. It turns out that one often wants to run more than one program at once. For example, consider your desktop or laptop where you might like to run web browser, mail, etc. In fact, a typical system may be seemingly running or even hundreds of processes at the same time. Doing so make the system easy to use, as one never need to be concerned with whether a CPU is available or one simply runs program. Hence our challenge, the crux of the problem, how to provide the illusion of many CPUs. Although there are only one physical CPUs available, how can the OS provide the illusion of nearly endless supply of said CPUs? The OS creates this illusion by virtualizing the CPU, by running one process, then stopping it and running another, and so forth. The OS can um, promote the illusion that many virtual CPUs exist when in fact there's only one physical CPU or a few. The basic technique known as time sharing or CPU of the CPU allows users to run as many concurrent processes as they want, as they would like. The potential cost is performance, as each will run more slowly if the CPUs must be shared. Okay, to implement virtualization of the CPU and to implement it well, the OS will need both some low-level machinery and some high-level intelligence. We call the low-level machinery mechanisms. Mechanisms are low-level methods or protocols that implement a needed piece of functionality. For example, I will learn later how to implement a context. We will learn later how to implement a context switch, which gives the OS the ability to stop running one program and start running another on a given CPU. This time share mechanism is employed by all modern OSs. On top of these mechanisms resides some of the intelligence in the OS in the form of policies. Policies are algorithms for making some kind of decisions within the OS. For example, given a number of possible programs to run on a CPU, which program should the OS run? A scheduling policy in the OS will make this decision, likely using historical information, which program has run more over the last minute, workload knowledge, what types of program are on, and performance matrix. The matrices is the system optimizing for interactive performance or throughput to make its decision. ماشي. طيب تعالوا نقرا البوكس كده، تقريبا في هايلايت هنا أو OSTEP use time sharing and space sharing. Time sharing is a basic technique used by an OS to share a resource by allowing the resource to be used for a little while by one entity and then a little while by another, and so forth. The resource is in question. The CPU or a network link can be shared by many. The counterpart of time sharing is space sharing, where a resource is divided in space among those who wish to use it. For example, disk space is naturally a space shared resource. Once a block is assigned to a file, it's normally not assigned to another file until the user deletes the original file. لو جينا نتكلم عن ال CPU virtualization، فهو عندنا شوية processes كده، فهو بيبدأ يهند شوية كده، يهند شوية بعد كده يهند شوية، وما بين الانتقال بيعمل حاجة اسمها context switch. طيب بالنسبة بقى للمساحة أو الستورج أو الميموري، لو هنتكلم عن اللي هو الميموري اللي هي اللي هو random access memory حاليا يعني، فهي بتكون ايه divided بشكل طبيعي، لأنه مش هينفع مثلا two processes يستخدموا نفس مكان في الميموري. يعني هو هنا time sharing، فالوقت انت شوية وانت شوية وانت شوية، اما المساحة او المكان زي ما في اوضة مثلا، كل حاجة بتاخد حيز معين وبتفضل ايه محتفظة بيه يعني، الا لو اتشالت بقى حصلها ديليشن او ايا كان. فده الوضع هنا. كده بقى ننتقل للجزئية التالية، هي the abstraction a process. The abstraction provided by the OS of a running program is something we will call a process. So البروسيس عبارة عن abstraction ل running program في operating system. As we said above, a process is simply a running program at any instant in time. We can summarize a process by taking an inventory of the different pieces of the system it accesses or affects during the course of its execution. To understand what constitutes a process, we thus have to understand its mechanism state, what a program can read or update when it's running at any given time, what parts of the mechanism of a machine are important to the execution of this program. One obviously component of mechanism and machine, I don't know why I mix up between these two words, of machine state that compromises a process is its memory. Instructions lie in memory as well. Thus, the memory that the process can address, called address space, is a part of the process. So يعني عندنا البروسيس فيها جزء كده اسمه address space، أو الجزء اللي واخده من memory يعني. Also part of the process's machine state are registers. Many instructions explicitly read or update registers, and thus clearly they are important to the execution of the process. address space ماشي. بعد كده عندنا الريجسترز. طيب طلعنا. Note that there are some particularly special registers that form part of this machine state. For example, the program counter. فعلى حد علمي يعني من آخر مرة بصيت في الموضوع ده، فاحنا عندنا CPU في بعض ال special registers، منهم PC counter والprogram counter sometimes called the instruction pointer or IB, tells us which instruction of the program will execute next. Similarly, a stack pointer and associated frame pointer are used to manage the stack for function parameters, local variables, and return addresses. Finally, programs often access persistent storage devices too, such as I/O. Information might include a list of the files the process currently has open. Tip: separate policy and mechanism. In many operating systems, a common design paradigm to separate high-level policies from low-level mechanisms. You can think of the mechanism as providing the answer to how question about a system. How. The mechanism answers a how problem. How does an operating system perform a context switch? The policy provides the answer to which question. For example, which process should the operating system run right now? Separating the two allows one easily change policies without having to rethink the mechanism, and is thus a form of modularity, a general software design principle. Okay. So we have the process API. Through we differ discussion of a real process API until a subsequent chapter. We differ discussion of a real process API until a subsequent chapter. Here we first give some idea of what must be included in any interface of an operating system. These APIs هنبص على API حقيقي في chapter قدام، يعني مفيش مشكلة. These APIs in some form are available on any modern operating system. Create a process. An operating system must include some method to create a new process. When you type a command into the shell or double click on the application icon, the OS is invoked to create a new process to run the program you have indicated. Okay, destroy as this type system call destroy as there's an interface for process creation. System also provide an interface to destroy processes forcefully. Of course, many processes will run and just exit by themselves when complete. When they don't, however, the user may wish to kill them. So and thus in an interface, to halt a runaway process is quite useful. خلونا نروح كده نشوف مثال عملي. نروح دلوقتي للديسكتوب وننزل OBS كده. لو فتحنا نحاول ايه دلوقتي نعمل زي process، بعد كده نعمل لها زي بيكل، او لو ان انا يعني اوقفها وانا اقتلها يعني. عايزين حاجة بتاخد بعض الوقت. خلوني مثلا ثواني كده أوقف وأشوف مثال ونظبط الدنيا كده. طيب معايا مثال لطيف كده، تعالوا نبص عليه. مرة تاني دو تول تو تيرمينالز اهمت. خلينا نجيب دي كده دي كده. في ملف اسمه demo دوت sh نو. الفايل ده كل اللي فيه ان هو بيفضل عامل دبي لوب، وبيطبع البي اي دي، وبعد كده البي اي دي ده اللي هو العنوان يعني بتاع البروسيس، وبعد كده بيسليب لسكند واحدة. فانا خليته اكسكيوتابل، فهعمل له run، فهيبدأ يشتغل اهو. بعد كده هعمله termination من instance تانية، يعني من هذه الايه التيرمينال. عملنا بس بيكل داش اف، ده اللي هو زي يعني ممكن نسميها طريقة ان انا اعمل باك للبروسيس. فانا وقفت البروسيس اهو. طبعا بقى مثلا لو احنا بنكتب كود او حاجة، فبالتالي طبيعة الحال بتكون الموضوع ايه مختلف. في زي هو بيبقى زي سيستم كول يعني مخصص لموضوع الايه الترمينيشن ده. تمام. طيب ويت، على حد علمي طبعا كل الكلام ده يعني دي كلها ايه حاجات من واقع مذاكرتي مش اكتر. wait sometimes، بعد كده السيستم كله اسمه wait. sometimes it's useful to wait for a process to stop running, thus some kind of waiting interface is often provided. برضه في سيستم كله اسمه wait. malicious control، آه بنطقها غلط، بنطق الكلمة دي غلط. خلوني كده اشوف الصحيح بتاعها. استخدمت يوجلش وبتنطق miscellaneous control. so ماشي، بدنا من اهوت. miscellaneous control other than killing or waiting for a process. There are sometimes other controls that are possible. For example, most operating systems provide some kind of a method to suspend a process, stop it from running for a while, and then resume it, continue it running. Status, there are usually interfaces to get some status information about process as well, uh, such as how long it has run or what state it is in. This is a diagram عندنا هنا الديسك في الستاتيك داتا و program. بعد كده بيقولك loading takes on disk program and reads it into the address space of process. كده نروح للميموري أو أهم. إنما البروسيس دي هتلاقيها stack فيها كود وليها لها stack وليب طبعا، فيها static data وفيها كود. وبعد كده بقى ايه المفروض ان السي بي يو بيبدأ ينظم يعني بيبدأ يعمل execution للinstructions، والاوبريتنج سيستم يبدأ ينظم الترتيب بتاع ال الترتيب بتاع الاكسكيوشن ده. process creation a little more detail. One mystery that we should unmask a bit is how programs are transformed into processes. Specifically, how does the OS get a program up and running? How does process creation actually work? The first thing that the OS must do to run a program to load its code and any static data initialize variables into memory into the address space of the process. Programs initially reside on disk. In some modern systems, flash-based SSDs in some kind of executable format. Thus, The process of loading a program and static data into memory requires the OS to read those bytes from disk and place them in memory um, somewhere as shown in figure 4.1. In early or simple operating system, the loading process is done early all at once before running the program. استنى كده الحتة دي. The process in early or simple operating systems, the loading process is done early, all at once before running the program. Modern OSs perform the process lazily by loading pieces of code or data only as they are needed during program execution. To truly understand how lazy loading of um, pieces of code and data works, you will have to understand more about the machinery of paging and swapping, topics we will cover in the future when we discuss the virtualization of memory. For now, just remember that before running anything, the OS clearly must do some work to get the important program bits from disk into memory. Once the code and static data are loaded into memory, there are a few other things the OS needs to do before running the process. Some memory must be allocated for the program runtime stack or just stack. As you should likely already know, C programs use the stack for local variables, function parameters, and return addresses. The OS allocates this memory and gives it to the process. The OS will also likely initialize the stack with arguments, specifically if it will fill the parameters to the main function argc and the argv array. ده طبعا في كود C. The OS may also allocate some memory for the program heap. In C programs, the heap is used for explicitly requested dynamically allocated data. Programs request such space by calling the malloc system in C and uh, free it explicitly by calling the free system call. The heap is needed for data structures such as linked lists, hash tables, trees, and other interesting data structures. The heap will be small at first as the program runs and requests more memory via the malloc library API. The OS may get involved and allocate more memory to the process to help satisfy such calls. The OS will also do some other initialization tasks, particularly as related to input-output I/O. For example, the in Unix systems, each process by default has 3 open file descriptors. I'll need to look in depth at this. Not for now. For standard input and output, these descriptors let programs easily read input from the terminal and print output to the screen. We will learn more about I/O file descriptors and the like in the third part of the book, Resistance. Okay, by loading the code and static data into memory, by creating and initializing a stack, and by doing other work related to I/O setup, the OS has now finally set the stage of program execution. It thus has one last task to start the program running at the entry point, namely main, by jumping to the main routine through a specialized mechanism that we will discuss next chapter. The OS transfers control of the CPU to the newly created process, and thus the program begins its execution. Process states. How many pages are left? Okay. Oh man, well, a lot to cover now. Process states. Now that we have some idea of what a process is, though we will continue to refine this notation and roughly um, how how it is created, let us talk about the different states of a process can be in at a given time. The notation that a process can be in one of these states arose in early computer systems. In a simplified view, a process can be in one of three states running in the running state. A program is running on a processor. This means it is executing instructions. Ready in the ready state, a process ready to run, but for some reason the OS has chosen not to run it at this given moment. And the last state is blocked. In the blocked state, a process has performed some kind of operation that makes it not ready to run until some other event takes place. A common example: when a process initiates an IO request to a disk, it becomes blocked, and thus some other processes can use the processor. لما نعمل مثلا اللي هو input في بايثون او scanf في سي او cn في سي اس بلس بلس، لو مستنيك تدخل حاجة للفاول بتاعك، فهو مستني كده، فالبروسيس ديت ايه بلوكد لحد ما الاي او ده يتم. If we were to map these states to a graph, we would arrive at the diagram. الفيجر ده بيوضح لنا الستيتس بتاعت البروسيسز. عندنا هنا اللي running، بعد كده هو ready scheduled running this schedules تبقى ready. عندنا هنا running ممكن تinitiate IO تبقى blocked لحد ما ال IO يتم، ترجع تاني تكون منتظرة ان يحصل لها scheduling، فبعد كده يحصل لها running. ماشي. As you can see in this diagram, a process can be moved between the ready and running states, and the discretion of the OS. ماشي. Being moved from ready to running means the process has been scheduled. Being moved from running to ready means the process is scheduled. Once a process has become blocked by initiating an IO operation, the OS has been scheduled. The OS keep it as such until some event occurs, IO completion. At that point, the process moves to the ready state again and potentially immediately to running again if the OS so decides. Let's take a look at an example how two processes might transition through some of these states. First, imagine those states running, each of which only use the CPU. They do an IO. In this case, a trace. The state of each process might look like this. عندنا هنا الأول التايم، لو دي تايم يونت أو حاجة. بعد كده عندنا البروسيس، زيرو بروسيس واحد، بعد كده دي ايه النوتس. ماشي. عندنا من واحد لأربعة بروسيس زيرو رانينج، وبروسيس واحد لسه موجودة في السكادجولر، أو هي already عليها الدور يعني، أو مستنية إن يحصل لها ايه execution يعني. أم، بعد ما واحد خلصت كده، بعد ما زيرو خلصت، واحد بقى هي اللي بدأت ايه ترن، وبالتالي ده التريسنج بتاعها يعني. In this next example, the first process issues an IO after running for some time. At that time, the process is blocked. Given the other process a chance to run, shows a trace of the scenario. عندنا هنا البروسيس زيرو شغالة شوية، بعد كده IO request ودي طول الوقت، بعد كده حصل بلوكينج لدي لحد ما ال IO تم، فديت كانت رانينج في نفس الفترة الزمنية دي. بعد كده ال IO done، فدي بقت ready، دي فضلت running برضه. طبعا بقى السكادجول هو اللي decides which run which is ready which is done، أو على حسب بقى هو خلصها ولا لأ يعني. بعد كده بعد ما خلص الأولانية دي ترجع للزيرو، هو عمل لها running تاني لحد ما بقت ايه done خلاص. ماشي. More specifically, process 0 initiates IO and becomes blocked, waiting for it to complete. Processes become blocked, for example, when reading from a disk or waiting for a packet from a network. Packet tracing بتاع. The OS recognizes process 0 is not using the CPU and start running the process 1. While process 1 is running, the IO completes. What's عودة إلى ما كنا عليه، خدنا بريك صغيرة لشرب كوب من الشاي. شرب مية، ونعود إلى ما كنا ايه نصنعه يعني. كنا واقفين عند الجزئية بتاعة الفكرة، اللي هو هنا أعتقد يعني. طيب بدون الاكتراث بقى الشخص اللي بقى عمال يصدر الإزعاجات دي، هنبدأ من أول هنا كده، ربنا يوسع يعني بقى جزء بسيط ونخلص قراءة هذا الشابتر. الشخص ده more specifically process 0 initiates an IO and becomes a blocked, waiting for it to complete process. أنا أعتقد خلصنا الجزء ده خالص، أو لا زي ما احنا ده. Processes become blocked, for example, when reading from a disk or waiting for a packet from a network. The OS recognizes process 0 is not using the CPU and starts running process 1 while process 1 is running. إنه توضيح يعني للفكرة ده شغال ازاي وكده. The IO completes moving process 0 back to ready. Finally, process 0 finishes and process 0 runs, and then it is done. Note there are many decisions the US must take, even in this simple example. First, the system had to decide to run process 1 while keeping while process 0 issued an IO. Doing so improves resource utilization by keeping the CPU busy. Second, the system decide not to switch back to process 0 when its IO completed. It is not clear if this is a good decision or not. What do you think? These types of decisions are made by the OS scheduler, a topic that we will discuss a few chapters in the future. Data structures. The OS is a program, and like any program, it has some key data structures that track various relevant bases of information to track the state of each process. For example, the OS likely will keep some kind of process list for all the processes that are ready, and some additional information to track which process is currently running. The OS must also track in some way blocked processes. When an IO event completes, the OS should make sure to wake the corrected process and ready to run again. Should make sure to wake the correct process and ready it to run again. Figure 4.5 shows 4.5. This one I think ناخد بص عليه دلوقتي. عندنا shows what type of information an OS needs to track about each process. In xv6 kernel, similar process structures exist in real operating systems such as Linux, Mac OS, or Windows. Look them up and see how much more complex they are. From the figure, you can see a couple of important pieces of information the OS tracks about process. The register context will hold for a stop process. The contents of its registers when a process is stopped. Its registers will save to the memory location. نجمع بس الدنيا كده. عندنا هنا from registers context. When a process is stopped, its registers will be saved to its memory location by restoring these registers, placing their value back into actual physical registers. The OS can resume running the process. We will learn more about that or this technique known as context switch in the future chapters. You can also from the figure that there are some other states a process can be in beyond running, ready, or and blocked. Sometimes a system will have an initial state that the process is in when it is being created. Also, a process could be placed a final state where it has exited but has not yet been cleaned up. In Unix based systems, this is called zombie state. ان شاء الله لو انا عملت مستقبلا فيديو عن اللي هو اليونكس شيل، يعني هي مبتبقاش فول فيتشرد وان، يعني بتبقى يعني تحاكي بس المجرد الفهم. فانا هنتعرض جامد لحوار الزومبي ستيت ده. هنشوف ان شاء الله مستقبلا يعني باذن الله. This final state can be useful as it allows other processes, usually the parent, the one created the process, to examine the return code of the process and see if the just finished process executed successfully or not. Usually programs return 0 in Unix-based systems when they have accomplished a task successfully, and non-zero otherwise. When finished, the parent will make one final call wait to wait for the completion of the child. Uh, okay, and to also indicate the OS that it can clean up any relevant data structures that referred um, to the now extended process. ممكن ناخد بص على الكود. The registers xv6 will save and restore to stop the subsequently restart a process. Struct. These are the names of these registers. The different states a process can be in: unused, sleeping, zombie, running. ماشي. The information xv6 tracks about each process including its register, context, and state. Point على الميموري. Size of process, memory, bottom of kernel stack. Process state BID ماشي. burnt process. boolean او integer value نتأكد هي killed ولا لأ. open files. current directory. context. ماشي، هو يعني السياق العام واضح، ولكن أكيد في بعض الخصائص تخص هذا الشيء يعني بعد غير محيط بها لسه. ربنا ييسر المستقبل نشوف. We have introduced the most basic abstraction of the OS, the process. It is quite simply viewed as a running program. With this conceptual view in mind, we will now move onto the nitty-gritty, the low-level mechanisms. Yeah, this is a funny way to say that. Something is daunting. ماشي، أيا كان. The low-level mechanisms needed to implement processes and the higher-level policies required to schedule them in an intelligent way. By combining mechanisms and policies, we will build up our understanding of how an operating system virtualizes a CPU or the CPU. قد وصلنا إلى نهاية هذه المعركة. دي حاجة للقراءة يعني. Key process terms. The process is the major OS abstraction of a running program. At any point in time, the process can be described by its state, the contents of memory in its address space, the contents of CPU registers, including the program counter, stack pointer, and among others. And information about I/O, such as open files, which can be read or written. The process API consists of calls programs can make related to processes. Typically, this includes creation, destruction. The other useful calls. Process exists in one of many different process states, including run and ready to run, or and block different events, getting scheduled or descheduled, waiting for an I/O to complete, transition a process from one of these states to the other. A process list contains information about all processes in the system. Each entry is found in these in sometimes called process control block, which is really just a structure that contains information about a specific process. دي بقى نهاية المعركة فعلا. بقالنا بنسجل بقالنا 50 دقيقة. أنا خدت بريك في النص وجيت تاني، فخدت بالنسبة لي وقت أكبر شوية، ساعة ونص تقريبا. أم، ولكن الأمر يستحق يعني. أتمنى يعني إن الطريقة دي تلقى قبول، أو يعني على الأقل ما تكونش مكروهة. شكرا على حسن المشاهدة. كان معكم محمد نبيل، ونلتقي في لقاءات أخرى إن شاء الله.